Let us start with half wave rectifier. We have seen so far the basic requirements of the rectifier circuits. Some parameters like average value, RMS value, ripple factor and loading effect, such points I discussed. Now let us start with the rectifiers. Okay, the half wave rectifier circuit appears in this fashion, and it is a step down transformer. As I said earlier, primary winding, and it is the primary winding and secondary winding, and the secondary voltage I am writing it like Vs, which is given by some Vm sin theta. I am writing, I can write sin omega t also, doesn't matter. I am writing Vm sin theta, secondary voltage. Okay, V primary voltage, AC input, V primary, and how is it working? Okay, so if you take this during the positive half cycles of the input voltage, during the positive half cycles, what happens? The anode of the diode is connected to positive terminal and the cathode is connected to the negative terminal. Diode is on, ideally acts as short circuit, and practically it maintains some voltage drop across it, or I can replace the diode by means of some resistance RF. Okay, so during positive half cycles, if we take diode is on, so that the equivalent circuit will be like this. Instead of diode, I am writing it by means of its equivalent resistance RF. Next, the load resistor RL is connected this way, and this is output, and I can mention the current IL flowing through the diode as well as the secondary as well as the load resistor. And what can we write for this IL? The IL is now given by the secondary voltage divided by the coil's internal resistance, secondary coil internal resistance denoted by RS, plus the diode forward resistance RF, plus the load resistance RL. Further, what is secondary voltage? It is Vm sin theta, Vm sin theta by Rs plus Rf plus RL. Further, I am taking this Vm by Rs plus Rf plus RL as some constant. I can write it like Im sin theta. So the current is looking like a sine wave. Okay, as secondary voltage is a sine wave and the current through the load, it is also a sine wave. And what about V output? V output is equal to IL into RL. It is given by Im sin theta into RL. Both are looking like sine waves. So this is what I have shown. Here V input or V secondary, it is something like some Vm sin theta. Then IL is given by, IL is equal to Im sin theta, and V output, it is equal to, right, IL into RL. Whose peak amplitude is Im into RL, that is Vm by Rs plus Rf plus RL multiplied with RL. So input secondary voltage has a peak amplitude of Vm, but output voltage has a peak amplitude of Vm into RL by Rs plus Rf plus RL. We can take it. And of course here it is the time axis, and I am mentioning the period also. Period of the signal I am writing it like 2 pi, right, 0 to pi and pi to 2 pi. Period I am writing period is equal to 2 pi. Okay, I can write period as capital T also, there is no difference. Okay, we can write capital T period is equal to some capital T, or I can take it like period is equal to 2 pi. The result remains the same. Right, anyway it is 0 pi 2 pi. Here I need not worry about writing it pi 2 pi etc. And of course from pi to 2 pi what is happening, 0 to pi I wrote, right, I showed this is secondary voltage IL and V output. Okay, then during the negative half cycle the secondary voltage is negative. During this negative half cycle what happens? Here I am writing during negative half cycles so it is like connecting a negative source. So that what happens is there, if you take the diode and the load resistor like this, is there any possibility for the diode to conduct? Just I am changing the polarities just to say that it is a negative half cycle. Okay, it is like connecting a negative source. So anode of the diode is connected to negative terminal, cathode of the diode is connected to positive terminal of the source. So diode does not conduct and it simply acts as open circuit. During negative cycles diode is off. Once the diode is off, it is simply acting like open circuit. So that is there any flow of the load current IL? IL is simply 0, so that our output is also equal to 0. I can say here VD, anode to cathode voltage, VD. Okay, so what happens here? The output load current is 0 and hence V output is equal to IL into RL, output is also 0. We can take it. IL is 0. Anyway, I need not further write it. Here we can understand. IL is 0 and hence V output is also 0. Again when positive cycle comes, the diode is on and IL is equal to Im sin theta and V output is equal to IL into R. Like this we can write. Again negative cycle IL is 0 and V output is also 0. This is how we can show output waveform. So what we did, we are converting the bipolar signal into unipolar signal. Very first step. Then what about the time period of the output current or output voltage? Its period is same as that of the input signal period. So from here to here it is 1 cycle and here to here it is 1 cycle. Okay, this is also fine. Now let us find the, okay, it is not a pure sine wave. So I can write here IL is equal to Im sin theta, that is true only for positive half cycle. Negative cycles it is simply 0. So for much precise, let me take this one. Im is the peak amplitude. According to Fourier series, the IL can be expressed as a sum of infinite number of sine and cosine waves along with a DC term. Or I can write it as a combination of DC and AC according to Fourier series. And V output is also can be written like a combination of DC and AC. Waveforms are similar, they have different amplitudes, nothing else, according to Fourier series, DC or average value. So how to find the DC components here? Now let me take the definitions here. Just during negative half cycles diode is off and hence V output as well as IL are 0. Now I am taking the IL equation like this. IL is equal to Im sin theta over the interval 0 to pi and 0 over the interval pi to 2 pi. Over one period I defined IL. Also I can write V output is equal to Im sin theta into RL over the limits 0 to pi and it is 0 over the limits pi to 2 pi. Now let us find IDC, VDC, IRMS, VRMS, etc. Some parameters we calculate. What are those parameters? Ripple factor, percentage regulation, ripple frequency, peak inverse voltage, efficiency, transformer utilization factor. Right? Every parameter has its own significance. What is the significance? After the calculation of the parameter, I will explain the significance and then you will understand what for I gave some prerequisites. I explained some prerequisites, some analysis, some explanations I did, what is meant by loading effect and ripple factor, etc. Okay, so V output is given by this. Now the next thing is, let us find IDC, average value or the DC component of load current. It is 1 by T integral 0 to T IL dt and it is 1 by 2 pi is the period, 0 to pi it is Im sin theta d theta plus from pi to 2 pi it is 0 d theta. Anyway, this value is 0. I have done this calculation earlier also. I am just repeating it, nothing else. It is Im by 2 pi integral sin theta is minus cos theta over the limits 0 to pi. Again minus Im by 2 pi into cos pi minus cos 0. How much do I get? Minus Im by 2 pi into cos pi is minus 1, again minus 1. Final result is Im by pi. The average or DC component of this waveform is IDC. It is Im by pi. It's an imaginary line. In a class, the marks of the students are varying this way. Then the average value IDC, it is equal to peak amplitude by pi. Okay, IDC we can write this way. And what about VDC? VDC is equal to IDC into RL, that is Im by pi into RL. What is Im? It is Vm by Rs plus Rf plus RL multiplied with RL multiplied with Y. Okay. From this equation, we can develop one Thevenin's equivalent circuit. We are taking the DC output voltage across the load resistor. Okay. From this equation, right, what I am saying is I would like to draw one equivalent circuit, which is known as Thevenin's equivalent circuit. what we can write. Like this we can write. You just check this circuit. If you observe this circuit, what is VDC? Vm by pi into RL divided by RS plus RF plus RL. How did I write this, draw this circuit? Anyway, this current is IDC. Okay. So, here, from the equation I am developing the circuit. Physically, do you have this circuit? No. The original circuit is this one. This is our transformer and diode, load resistor, etc. But from the equation we have got, I am drawing the Thevenin's equivalent circuit. And what about the Thevenin's equivalent voltage? So the voltage looking into RL, it is VTH, it is equal to Vm by pi. And the resistance looking into this circuit excluding RL, what is the resistance looking into RL? That is RS plus RF. RTH is equal to the coil's internal resistance, secondary winding internal resistance RS plus the diode forward resistance RF. We can take like this, the Thevenin's equivalent. Physically it is not existing. We are writing it from the equation for VDC we have got. From that equation we developed a circuit. From that circuit we are writing these two values, Thevenin's and R Thevenin's. Okay. Next, RMS value. The RMS value of the current is given by root mean square. It is further written like 1 by period is 2 pi and over the limits 0 to pi it is Im sin theta, means Im square sin square theta d theta, from pi to 2 pi 0 d theta. Anyway, this term is 0, we need not worry about it. It is further written like Im square by 2 pi integral 0 to pi sin square theta can be written like 1 minus cos 2 theta by 2 d theta. And further Im square by 4 pi into, it is theta minus sin 2 theta by 2 over the limits 0 to pi. So what do we get here? It is Im square by 4 pi into pi minus 0. Sin 2 pi is 0 minus sin 0 is 0. So final here the result is 0. So what is the final answer? It is Im by 2, IRMS. RMS value of the current. It is Im by 2. It is not Im by root. If it is a pure sine wave, then RMS value of the current might be Im by root. It is not a pure sine wave, it is a half sine wave. Okay. Fine. Then once I know the RMS value of the total current and its average value, okay, I can write the RMS value of the AC component. IAC I mentioned, no? IL is combination of DC and AC. RMS value of IL is known and DC component is known. Then I can write the RMS value of AC component. AC component is given by, I told you that formula, IRMS dash, it is equal to square root of IRMS square minus IDC square. And IRMS, what is IRMS? It is IM by 2 whole square minus IDC IM by pi whole square. We can write this RMS value of AC component. Okay. Then once I know this, the first parameter I am calculating is ripple factor. Ripple factor RF is equal to, it is just nothing but the amount of unwanted AC present in output by the DC value. Okay, VAC, unwanted component in the output, it is VAC. It is further written like IAC into RL by IDC into RL. So I can cancel R and RL. Even though I write IAC, we do not know it. At the time of substitution, what should we write? It is a RMS value. So it is further written like IRMS dash by IDC. RMS value of AC component by DC component. And it is even further written like square root of form factor square minus 1, or it can be, right, its value is already written, or I can even further write it like it is square root of form factor square minus 1. What is form factor? It is IRMS by IDC whole square minus 1. What is IRMS? It is IM by 2 whole square by IM by pi whole square minus 1. It is further written as square root of pi square by 4 minus 1. If you further calculate it, it is 1.21. It is a standard value of a rectifier. It's not dependent on the time period or the amplitude of the secondary voltage or the output voltage or the load current. Once the waveform of the signal is like this, then the ripple factor is 1.21, independent of its amplitudes, time period, etc. It's a standard value. Okay, what is the significance of this ripple factor? Why we are calculating it? Just earlier I mentioned some definitions and I am now substituting. Here my concern is to find, to convert AC signal into DC. But here what is happening? The entire AC is not converted into DC. This is our AC signal, right? This is our AC signal. And the DC component we are getting is only this much. This is the only DC you are getting. Okay, what you are doing first, you are converting this AC into pulsating DC or bipolar signal into unipolar signal, and that unipolar signal is not completely a DC component, it is a combination of DC and AC. And this unwanted AC, we are expecting only DC, but we are getting some AC which is known as unwanted AC. Or it is also known as ripple signal. And what about this IDC? Peak amplitude by pi. Okay. So why we are calculating ripple factor means this unwanted AC by DC component you are writing. My concern is to see that the AC component is as minimum as possible and DC component is as large as possible. Ideally, there should not be any AC component. I want only DC. Okay, is it possible at this stage? No. It is a combination of DC and AC, and the AC component is what is the amount of that AC component along with the DC present in the output. Means for that you are taking this parameter ripple factor. Ideally, the AC component is 0, DC component should be maximum, and hence the ripple factor should be 0. Ideal case. practically, as far as the current example is concerned, we are getting the ripple factor as 1.21. Okay, it's a larger value. We should not get such larger value. Anyway, we have started with a very basic circuit. Obviously, you can see such larger value. We will keep on modifying the circuit till we get very less value of ripple factor, 0.001. Such small values are possible. Okay, so this is the first parameter and its significance. Why we are calculating? Anyway, earlier in my previous class, I just gave mathematical explanations, derivations, etc. Now you can understand. In the rectifier, our concern is to convert AC into DC, but secondary voltage is a pure AC signal, but output is not pure AC. Output is a combination of DC and AC. And so in the output, what is the amount of AC present, and what about the DC component? Amount of AC by DC, that is defined as the ripple factor. Ideally, its value should be 0, but practically it should be as much small as possible. And in this example, if you calculate the ripple factor, it is found to be 1.21. It is a standard value, and this value does not dependent on the amplitude or frequency of the input or the output. It is a standard value. This is the very first parameter. The second one, peak inverse voltage. It is also denoted by PIV. Peak inverse voltage, what it means? The peak or the maximum voltage. Appearing across diode under reverse bias condition. In reverse bias, what is the peak or the maximum voltage appearing across the diode? Okay, that is known as peak inverse voltage. Peak inverse means in reverse bias, that's the meaning of it, peak or maximum voltage across the diode. So reverse bias means during negative cycles only the diode is reverse bias. Let us take during negative cycles. We know during negative cycles diode is off, so the equivalent circuit we take is this way. RL, secondary voltage. Is there any current that is possible here? No. And voltage across the diode from anode to cathode, I am writing RL V output. So if I take the loop equation, Vs is equal to voltage across the diode plus V output, where V output is equal to IL into RL, whose value is 0. Means whatever the secondary voltage you have, entire secondary voltage is appearing across the diode, which implies Vd is equal to Vs. Means the entire secondary voltage, this particular portion, this portion or this complete negative cycle can be seen across the diode. Okay, so if you want, we can even show that also diode voltage. First two cycles, the diode is almost acting like short circuit, negligible voltage. First two half cycles, almost the diode acts as short circuit, and almost all the secondary voltage can be seen across the output terminals. And during negative cycles, whatever the secondary voltage we have, that entire secondary voltage can be seen across the diode. its peak amplitude minus. Again positive half cycles, almost the diode voltage is 0. Practically there is small voltage around 0.7 like that, some drop across RF. Again negative cycles, the entire secondary voltage can be seen. Again positive cycles, diode voltage is 0. Negative cycles, the entire secondary voltage can be seen across the diode. So anode to cathode voltage is negative, diode is off. That's the meaning of it. Then peak voltage, what is the peak voltage? That is minus Vm, or the maximum voltage magnitude I am taking, appearing across the diode under reverse bias condition. Peak or the magnitude of the voltage. Okay, the maximum voltage appearing across the diode under reverse bias condition. What is that? It is Vm. Anyway, Vd is equal to Vs. It is Vm sin theta. The equation may be like this, but it is during negative cycles, means Vd is negative. So what is our peak inverse voltage? It looks like minus Vm, but we take the magnitude, that is Vm. Peak inverse voltage is equal to Vm. What for we are calculating this parameter? You see, the idea here is, if you look at the diode, it is conducting for positive cycles and allowing the entire signal to pass through it. During negative cycles, diode is open circuit, diode is objecting the signal and it is holding it. Positive cycle, what happens? The entire signal is sent to the load resistor. The diode is supporting in sending the entire secondary voltage to the load resistor during positive cycles. When negative cycle comes, the diode is acting as open circuit and holding the entire secondary voltage. It is holding. Okay, this entire negative cycle is appearing across the diode. That's the meaning of it. Again positive cycle comes, it is sending the entire signal, so that you are getting an output voltage waveform of this kind. Input is a bipolar signal, output is unipolar, and which is a combination of DC and AC. So you can able to create some DC component at the output, whereas secondary voltage or the input to the rectifier is a pure AC signal. Vm sin theta, it is pure AC. Bipolar signal. We convert it into unipolar so that you can able to generate some DC current as well as DC voltage across the load resistor. Okay, it is fine. So during negative cycles the diode is objecting. If the diode doesn't object during negative cycles, then you will get some output voltage during negative cycles also, something like this. We do not know what comes. As the diode is not allowing, then what about the average value? IDC will be less than Im by pi, or VDC is less than Vm by pi if during negative cycles, if the diode conducts. But here the diode is unipolar, right, unidirectional device. It doesn't allow the flow of current in the opposite direction. It allows flow of current only in one direction. That property we are using in generating some DC. So we have got some DC. So during negative cycles, diode is taking the responsibility in holding the signal. That's what, right? And how much? What is the, right here we are calculating what is the peak voltage the diode is handling. Why we are calculating it means, calculating this one means it is ready to hold the signal. It doesn't mean that any amount of signal you can give. So if the amplitude Vm of the secondary voltage is more, automatically peak amplitude is more, means the DC component IL peak amplitude will be more and V output peak amplitude also will be more, so that IDC will be more. To have larger amount of DC currents or DC voltages across RL, the secondary voltage amplitude should be high. Okay, it is fine. At the same time, when negative cycle of comes, that entire negative cycle is appearing across the diode. Diode is taking the responsibility in holding it. If you use a secondary voltage of very large amplitudes, then that large magnitude is appearing across a signal with large magnitude is appearing across the diode during negative cycles. That may lead to some avalanche breakdown. If the avalanche breakdown takes place, then diode starts conducting the negative cycle as well. If the diode conducts, then then the average value falls down. The output current as well as voltage are a combination of AC of both positive and negative cycles, which reduces the DC component of overall result. So our concern is to have maximum DC, for which we try to choose the larger amplitude of the secondary voltage. At the same time, what happens is that large amplitude during negative cycles, it is appearing across the diode, which may cause avalanche breakdown, or even sometimes it may cause the diode to burn. After once avalanche breakdown takes place, it may lead to burning of the device. It's possible. Avalanche multiplication, we say. Okay, so we should avoid that. Objecting the signal, holding the signal is a good habit. It doesn't mean that we can apply any signal of our choice. If you apply very large amount of signals with large amplitudes, that will damage the diode, or that will reduce the average value of your result. Okay, so that's why we are calculating and how much is the peak amplitude the diode is experiencing. That's what we are measuring, so that we can be careful with respect to the avalanche breakdown voltage of the diode, or in maintaining good average value of the output voltage. These are the concerns why we are calculating the peak inverse voltage. The next parameter is percentage regulation, or I can say voltage regulation. What is meant by percentage regulation? I can even write it like percentage regulation is equal to VDC no load minus VDC full load by VDC full load multiplied with 100. Okay, equation wise it is fine. What is meant by VDC no load? Earlier I explained loading effect. If RL is small, IL is large, output voltage will be small. If RL is large, IL is minimum, then we can see the maximum value of output voltage. When output voltage's amplitude is more, the DC value will be more. It's a simple thing. So that voltage is known as no load voltage, VDC no load, we can say. So here, if RL is maximum, then IL is minimum. If IL is minimum, I can say minimum loading effect. If IL is minimum, then V0 is maximum. Output amplitude will be maximum. If V0 is maximum, obviously VDC will be maximum. Implies VDC is maximum. So when RL is maximum, we can see maximum VDC. That DC is known as VDC no load, known as this one, known as VDC no load. Minimum loading effect, no loading effect, I can say. Okay, so it is given by, implies VDC no load is equal to Vm by pi into RL is maximum, means RL maximum by RS plus RF plus RL maximum. Now here generally RL is at its maximum value, means IL is at its minimum value, minimum loading effect. So as RL is extremely high, I can say RS plus RF is far less than RL maximum. It is possible. Then VDC no load, it is equal to Vm by pi into RL maximum by RL maximum. It is equal to Vm by pi. approximately I am writing. Okay, as RS plus RF is extremely less when compared to RL maximum, then VDC no load is approximately equal to this. It is a valid approximation. We are increasing RL such that IL is about to become 0. Okay, that's the meaning. It's not like simply removing RL. We cannot make RL infinite. If RL is infinite, then the circuit is no more a rectifier. The diode never conducts at all. Okay, and output is always equal to secondary voltage. Okay, so we cannot take that way. Okay, we are increasing RL such that IL is about to become 0, so that V output is maximum and the corresponding DC voltage is also maximum. Okay, IL cannot be 0, it's approaching 0. This is the meaning. You cannot take RL is equal to infinite. RL is at its maximum value. If you take RL is infinite, then diode will never conduct and there is no point of analyzing the circuit at all. Okay, this is one. And VDC full load. Full load means loading effect is maximum. When is it possible? When RL is minimum, IL is maximum. And the corresponding output is minimum. That is known as V out. Okay, the corresponding DC output voltage is known as VDC full load. So let me write that also. If RL is minimum, the corresponding IL is maximum. That is known as maximum loading effect. That makes V output to be minimum, right? Which implies when V output is minimum, the corresponding DC is also minimum. Once DC is minimum, that is known as VDC full load. The DC voltage only with maximum loading. Okay. So this is how we can write it. And what for we are calculating? In a rectifier, there is a scope for the load resistor to vary. If the load resistor varies, it may be small or large, our output, if it is large, then we get more DC. If RL is small, less DC. But my concern is I should get the best possible DC output voltage independent of the load resistor. RL may be small or large, I want the best result. Is it possible here? No. There is a difference in both the results. What is that difference? The difference should be as minimum as possible. If the difference is maximum, the circuit is not performing good. Once I am designing a system means I should not blame load resistors, right? As you kept a smaller value of RL, you are getting less DC output voltage. No. RL may be small, RL may be large. My design is in such a way, should be in such a way that output voltage is maximum, which is not happening so in this case. Okay, that's why we are calculating this parameter. So the percentage regulation, now it is given by VDC no load, Vm by pi minus VDC full load. Okay, I did not write here, no? VDC full load, I should write it. VDC full load, it is equal to Vm by pi into RL minimum by RS plus RF plus RL minimum. Here I cannot write RS plus RF is far less than RL minimum. Earlier RL maximum I can say. Okay, then implies the percentage regulation, it is equal to no load voltage Vm by pi minus full load voltage Vm by pi into RL minimum by RS plus RF plus RL minimum by Vm by pi into RL minimum by Rs plus Rf plus RL minimum into 100. I can cancel Vm by pi both sides. Then further we can write it like Rs plus Rf plus RL minimum minus RL minimum by RL minimum whole thing divided by RL minimum by Rs plus Rf plus RL minimum. Further I can cancel this term and this term. These two will be gone. So it is Rs plus Rf by RL minimum. That's it. This is the formula for percentage regulation. Regulation should be as much small as possible. Ideally 0. Practically it should be as much small as possible. Okay. Ideal value of percentage regulation is 0. But practically percentage regulation should be as much small as possible. That's it. That's why we are calculating this parameter, percentage regulation. Okay. Next one. Three parameters we calculated. Next one is efficiency. It is denoted by eta. Okay. So efficiency, conversion efficiency. Input is AC, you are producing DC. So what is the amount of DC you are producing from the AC input you are applying? That's what is called conversion efficiency. So the percentage efficiency is equal to DC output delivered to the load by AC input multiplied by 100. And what about the DC output? PDC. DC output, it is equal to IDC square into RL. IDC is Im by pi whole square into RL. Okay. Then what about the AC input? That's my question. Okay. How do we find it? AC input means. See, I have this rectifier circuit. It is Vs we are writing, and I wrote it like IL. So what is the power generated across the secondary winding? Power generated across secondary winding. Okay, or P AC rated secondary, I can say secondary power. It is just nothing but Vs into IL. I can write it. Vs is Vm sin theta and IL is equal to Im sin theta. But what is its value as far as this value is concerned? Equation wise we may write it like this, but at the time of substitution we should write its RMS value and its RMS value. What is the RMS value of secondary voltage? Secondary voltage is a pure sine wave, right? Secondary voltage Vs or V input, it is a pure sine wave. Its RMS value is peak amplitude by root 2. And RMS value of load current, I calculated it already. It is Im by 2. Okay, so Vm can also be written like Im into Rs plus Rf plus Rl multiplied with Im, so Im square by 2 root 2. Okay, the power generated across the secondary winding. It looks like AC input power only. Okay, let it be. It is the power, it is also known as the source power. Power generated across the source, secondary winding. Okay, circuit power I am taking. Circuit power means the power dissipation across secondary coil's internal resistance and diode forward resistance and RL. I am taking like the circuit power. Power delivered to the circuit. Circuit power or power delivered to the circuit. Okay, I can write it like P circuit. It is just nothing but IL square into RS across the secondary coil winding plus IL square into the diode forward resistance plus IL square into RL. The power delivered across each of the resistors. Okay, so even though I am writing IL square, what we write at the time of substitution, we should write its RMS value, or I can write IRMS square into RS plus RF plus RL. IL square into RS plus RF plus RL, where IL instead of IL we should write its RMS value. It is equal to IRMS, it is equal to Im by 2 whole square into Rs plus Rf plus RL, or it is Im square by 4 into Rs plus Rf plus RL. Is this circuit power is equal to source power? No. Numerator is same. Here the denominator is 2 root 2. Here the denominator is 4. Okay. Generally, what do you expect? Always what we expect is, under ideal conditions, the power generated at the source is equal to power absorbed by the circuit. Is it not so? But here power absorbed by the circuit is different from, it is less than the power generated or power delivered by the source. There is a conflict. In that case, what should I take as my input voltage? And why you are getting it so? Why you are getting two controversial things, two different answers? Because just as an example, I am taking, I have one circuit like this, some 10 volts, 4K, 6K. So the current flowing is 1 milliampere. The same example I took so many times. This is our input. Okay, so V input is equal to, if I take the loop equation, voltage across 4K plus voltage across 6K. Okay, it is 10 volts and it is 4 volts and it is 6 volts. Everything is fine. Now I am multiplying both sides with I. V input into I is equal to voltage across 4K into I plus voltage across 6K into I. What is V input? It is 10 volts into 1 milliampere it is 4 volts into 1 milliampere plus 6 volts into 1 milliampere. Means it is 10 milliwatts is the source power. And it is circuit power. Whatever the power generated at the source, that is delivered to the circuit. So under ideal conditions, the entire power is distributed among the resistors. So it is a source power I am writing. Source power is equal to circuit power. It is a DC. It need not be DC, it can be AC also. Right? Let us take a similar case like 10 sin omega t, 4K, 6K, let this current be I. Again here also I can write V input is equal to voltage across 4K plus voltage across 6K. It is as usual 10 sin omega t, and it is 4 sin omega t and 6 sin omega t. Okay. Multiply both sides with the current. V input into I is equal to voltage across 4K into I plus voltage across 6K into I. It is just nothing but the source power. Even though I am writing it like this, at the time of substitution we write their RMS values. So it is V RMS into I RMS is equal to voltage across 4K, the same thing. It's RMS value of this and RMS value of this. Okay, at the time of substitution. So here if I take it, so how much you are getting? RMS value of this voltage. It has no diodes, nothing, right? Simple thing. Vm, it is 10 sin omega t, and I is equal to what we can write 1 sin omega t milliampere. Okay, so V input, its RMS value is 10 by root 2 into, it is 1 by root 2 milliampere. It is equal to 4 volts. 4 sin omega t means 4 by root 2 is its RMS value, and RMS value of current is 1 by root 2 milliampere. Next, it is 6 by root 2 into 1 by root 2 milli. So how much do you get? It is 5 milliwatts is equal to 2 milliwatts plus 3 milliwatts. Absolutely. So it is the source power or power generated at the source. And here it is known as circuit power or power delivered to the circuit. Source power is equal to circuit power. Whether you take a DC source or AC source, this is true. Instead of sine wave, you can give triangular wave. What is there in it? Then triangular wave of peak amplitude some 10 volts. Then what happens? 10 by root 3 into 1 by root 3 into 10 power minus 3. The same way we follow. Let it be. So here always it looks like the source power is equal to circuit power. But in this case, if you take the rectifier circuit, the source power, the power generated at the source is not equal to the power generated, power delivered to the circuit. Both are not same. What is the reason? The reason is the switching element diode. When there is a switching in a circuit, here there is no switching. The current is continuous for all time. Here also the current is continuous for all time. Both the cases. But in the rectifier, IL is existing for only positive cycles. IL is not existing for all time. When there is a switching, here what happens is the diode acts as a switch. When the switch is closed, that time IL is existing. When switch is open, IL is 0 and V output is also 0. When there is a switching, that time you cannot write, when there is a switching, then we cannot take the source power is equal to circuit power. Or source power or power generated at the source. Or source power is not equal to the power delivered to the circuit or power absorbed by the circuit. Power delivered to the circuit, or I can also known as circuit power. When there is a switching, you cannot equate them, meaningless. That's why the source power, it is also, what is this? In this example, we got PAC rated secondary, whose value is already seen. And the second one is power delivered to the circuit. It is known as AC input power. Both are not same. Now what is efficiency? Efficiency we write with respect to the AC input. So now coming to the percentage efficiency, it is equal to DC output power. Okay. Due to switching only, they are not equal. In any regular networks, if I take whether you give AC input or DC input, in any network, always the source power is equal to circuit power, or the power generated is equal to power absorbed. Okay. But in this case, it is not so due to the switching of the diode. It is diode switching. Diode switch. Then coming to the AC efficiency, what you expect is output DC power by AC input power. AC input means secondary voltage. This is power generated across the secondary winding. You cannot take it. Okay, there is another thing like the power generated, power delivered to the circuit. So that's what we are taking. So DC output, it is Im square by pi square into RL by power delivered to the circuit. It is Im square by 2 into Rs plus Rf plus RL multiplied with 100. Okay. Im by 2, sorry, it is Im square by 4, no? 4, not 2, it is 4. So Im square cancel, and I can even write it like 4 by pi square, or 400 by pi square into RL by Rs plus Rf plus RL. It is even further write it like 40.6 divided by 1 plus Rs plus Rf by RL. Conversion efficiency with respect to the power the circuit has taken, it is nothing, it is coming around 40.6% conversion efficiency. Okay, and whereas there is another parameter known as transformer utilization factor. Means with respect to the original source, what is the conversion efficiency? Anyway, output is DC and the input, if I directly take the power across the secondary winding, then what is the conversion efficiency? That is known as transformer utilization factor. It is known as TUF. So the percentage TUF, transformer utilization, it is output DC power, DC output power by PAC rated secondary, means the original source power you are taking. We are calculating efficiencies only, conversion efficiencies only. In one case, what I am taking, the power absorbed by the circuit as denominator. In the second case, the original source power in the denominator, conversion efficiency. So DC output, it is Im square by pi square into RL by, it is Im square by 2 root 2 into Rs plus Rf plus RL multiplied with 100. Im square cancel 2 root 2 or 200 root 2 by pi square into RL by RS plus RF plus RL. Okay, pi square is approximately 10, so it is 20 root 2 means it comes around 28.28 divided by 1 plus RS plus RF by RL percentage. We can take. With respect to the original source, the conversion efficiency is less because the source power is no doubt greater than the circuit power. Okay, here what is the source power? It is Im square by 2 root 2 into Rs plus Rf plus RL. That is the source power, right? And circuit power is no doubt less than source power. How can we get circuit power more than source power? Meaningless. Circuit power is less than or equal to source power. So the numerator remains the same while calculating the efficiency. Right? If you use the circuit power, definitely it comes a value which is greater than the value you are getting with the source power in the denominator. So this is the idea. Ideally, what you expect, efficiency should be as much large as possible. Maximum DC I should get from the AC input. In this example, it is not happening so. With respect to the secondary winding, it is just 28%, and with respect to the power the circuit has taken, absorbed, the DC power produced at the output, the conversion efficiency is 40.6%. Nothing to worry much about the denominator. So this is the idea. Every parameter, now just like that we don't calculate. Every parameter has its own significance. Okay. Coming to the last one, ripple frequency. It is the frequency of the unwanted AC component. It is nothing but the frequency of unwanted AC component. VAC or ripple component. It is frequency of the ripple signal, we say. Unwanted AC, other name for unwanted AC is ripple component. Okay, so if you take V output, see the waveforms. The output waveform is this way. Okay. Then what about its AC component? AC component is invisible, to be frank. If you want to find it, again we have to use a Fourier series expansion, etc. It's a very lengthy. Without knowing AC component, we could able to calculate its RMS value, VAC or VRMS dash, right? IRMS dash. We calculate it. Let it be. So here the ripple frequency means the frequency of this unwanted component. The frequency of this unwanted component and frequency of output are one and the same because DC it is a constant. And what about the output frequency? Output frequency is same as that of the input signal frequency. The input time period is 2 pi and output voltage time period is also 2 pi. Means the output period and AC component period will be automatically same. So the frequency of unwanted AC component VAC, it is nothing but the frequency, in this example, frequency of V output. And output frequency in this case is same as that of frequency of input. Okay, output ripple frequency and the input signal frequency are one and the same. What is its significance? Anyway, for this particular parameter, we need to wait for couple of circuits. Down the line, I will explain its significance, ripple frequency. Okay, so we calculated here some parameters. As far as this half wave rectifier is concerned, I calculated, right, first, anyway, I calculated IDC. It is Im by pi. From that, VDC is also calculated. It is not Vm by pi. It is Vm by pi into RL by RS plus RF plus RL, the summary, right? And IRMS we calculated. It is Im by 2. From this, we calculated ripple factor. It is found to be, right, anyway, IRMS dash, RMS value of AC component, it is IRMS square minus IDC square. Ripple factor is found to be 1.21. Okay, from these values we calculated some parameters like ripple factor, and the second one is peak inverse voltage. It is Vm. And what is its significance? We have seen. Next, percentage regulation. It is equal to RS plus RF by RL into 100. Okay. Ideally, we expect ripple factor should be as much small as possible, but in this case, we are getting some standard value 1.21. Percentage regulation like this. It also should be as much small as possible. The concern behind percentage regulation is if RL changes, then output peak amplitude keeps on changing. RL minimum, of course, which is not supposed to happen. Okay. And the fourth parameter, the percentage efficiency. There is a difference between efficiency and transformer utilization factor. It comes to be 40.6 by 1 plus RS plus RF by RL, or 40.6%. Next one is the percentage TUF, transformer utilization factor. It is 28.28 or 28.3 something, I can write it, by 1 plus RS plus RF by RL. And finally, the ripple frequency, the unwanted AC components frequency. It is same as that of frequency of input signal. Right. These are the 6 parameters I calculated. Please observe the difference between efficiency and TUF. Due to the diode switching, diode acts like a switch. Positive cycles it is on, IL is flowing. Negative cycles it is off, IL is not flowing. In that case, when there is a switching, you cannot equate the source power to circuit power. That's why we are calculating 2 parameters. With respect to the source power, what is the conversion efficiency? With respect to the circuit power, power absorbed by the circuit, what is the conversion efficiency? Okay, this is the idea. That's about the half wave rectifier. And what are the difficulties here? Ripple factor is very small, sorry, very large. We are expecting that to be as much small as possible. And conversion efficiency or transformer utilization factor, they are also very less. I have to reduce the ripple factor and I have to improve the conversion efficiency. Okay, peak inverse voltage and all. Okay, peak inverse voltage should be small as far as the avalanche breakdown voltage is concerned. It should be high, right? It should high means it is objecting the signal. That's a good thing. At the same time, it should not reach the avalanche breakdown voltage. That's the idea. Percentage regulation should be as much small as possible. That's it. That is about the half wave rectifier. So now to overcome the drawbacks of ripple factor, conversion efficiency, TUF, we are going to the next circuit, that is center tapped full wave rectifier.